Hello and welcome to another Smart Grid Systems class. Today we're going to talk about renewable energy, and then we'll spend a good amount of time on hydropower. This is an important topic in smart grids because power systems are moving more and more toward cleaner energy sources. So first I will give you a general overview of renewable energy, and then we'll focus on how power works and why it is still so important. So today's topic, as mentioned, is renewable energy. You hear this term all the time, but in power system, it has a very specific meaning. These are energy sources that can naturally be replenished, unlike fossil fuels. We'll start broad and then narrow down into hydropower today. So renewable energy, what is renewable energy? Renewable energy basically means energy that comes from sources that are naturally replenished. So we're talking about things like wind, solar, biomass, hydro, and geothermal. The big idea is that using these resources doesn't permanently use them up the way burning coal or natural gas, for example, does. And nature keeps replacing them. So why do we care so much about renewable energy? First, fossil fuels are limited, so they won't last forever. Second, renewable energies are cleaner, so they help reduce pollution and greenhouse emissions. That's better for environmental and also better for the public health as well. Another big reason is cost. Over the years, solar and wind especially have become much cheaper, so renewable energy is no longer just an environmental choice. It also makes economic sense as well. This slide gives us the big picture globally. Fossil fuels still make up most of the world's energy use, but renewables are an important and growing share. Also notice that renewable energy is not just one thing. It includes hydro, wind, solar, biomass, geothermal, and more. And some countries like Iceland rely a lot more on renewables because of the natural resources they have available. Specifically, they have a lot of geothermal. Now, renewable energy is used in a lot more places than just electricity generation. It can be used for example for heating and cooling, transportation, off-grid systems, and of course regular electric power generation. So we can talk about renewables. We're talking about so when we're talking about renewables, we're talking about a broad energy solution, not just solar panels on rooftops. Now, we're narrowing the focus to electricity generation in this class. These charts show where the words electricity comes from. Coal and natural gas are still major contributors, but renewables are growing. This is important because electricity is becoming a bigger and bigger part of how we run society, especially when electric vehicles, smart homes, and electrification comes in picture in general. Now, this slide shows energy use in US by sector and also shows how electricity has become more important over time. A larger share of our total energy use now comes through electricity than it did decades ago. That means if we make electricity cleaner, we can make a lot of the whole energy system cleaner too. So you can see it was 10% in the 40s, 25% in the 70s, and 40% in the 30s, and uh, it's going up, the percentage of electricity over primary energy consumption. Now, this graph shows how the US electricity mix has changed over time. Coal used to dominate for many years, but over time, natural gas, nuclear, and renewables started to take larger shares. So the main point here is that the grid is always changing. It's not fixed. Technology, economics, and policy all push the generation mix in different directions. This is a more updated view, and you can clearly see some major trends. Um, Coal here, as you can see, has dropped significantly since 2001. You can see it went from around 2 billion megawatt hours to less than zero point 0.8 billion. So you can see, as mentioned, coal has gone down a lot. Natural gas has grown because of the fracking and the shale revolution, and now U.S. is a net exporter of gas. Actually, it produces a lot of ag gas. It's clean, much cleaner and cheaper than coal. And also you can see that renewables have also increased. Hydro and other renewables you can see has increased significantly over the past 2 decades. So when people talk about the energy transition, this is what they mean. The power system is shifting over time toward different resources. Now, this is U.S. generation or U.S. electricity generation from 2017 to 2020, just two uh, time frames 3 years apart. You can see how it has been changed. The renewable went from 17 to 20%. Nuclear didn't change. Coal went down from 30% to just 19%, and natural gas went up from 32 to 40%. This comparison is nice because it shows how quickly things can change in just a few years. Natural gas increased, coal went down, and renewable kept growing. So the electric grid really is evolving pretty fast. And that one reason why smart grid technologies are so important. You can see it just in a 3 year span, you can see how it has shifted significantly. Um, in this slide, we are looking only at renewable electricity in the US. And blue is hydropower. You can see yellow is solar, green is wind, orange is geothermal, and brown is biomass. Um, and as we as shown here, hydropower has been the biggest renewable source for a long time. But wind, you can see wind has grown significantly. Um, so hydro is still very important, but now it's part of a larger renewable mix. And you can see this pie chart showing the portion of each energy source. You can see now it's wind is now around 37% now. It's actually more than that. That's uh, not very updated data. This figure shows renewable electricity generation over time. The biggest thing you should notice is the strong growth in wind and solar. Hydro has been steady. You know, you can see it sometimes goes up and down. The reason is if there is a drought season or a rainy season, hydropower fluctuates. Obviously, when you have a drought season, you can't open the dams, and when you have a rainy season, you can use more of that power. And you can see that the average for hydro has stayed flat because we have dammed all the rivers that we could. And we put dams on all the rivers and use the energy for them. Actually, they're tearing down a lot of dams. The reason is because environmental impact. Some of them have a huge environmental impact, so they're tearing them down. They prevent fish migration and so on. They have huge impact on the ecosystem. So that's the reason we reached the peak of the hydro energy. You can see around the 80s, the mid 70s and 80s, we reached a peak. So we have built all the dams that we could on the rivers and the water systems. Um, yeah, but wind and solar, they have expanded and still have a lot of uh, space to expand as well. This chart gives a future-looking scenario. If the US moves towards net zero emission, then solar and wind are expected to become huge parts of the electricity mix. You can see the growth in solar and wind. and compared to hydro. This is a projection from 2020 to 2050. Uh, Hydro and nuclear are so important because they help with reliability and stability. Again, wind doesn't always blow and the sun doesn't always shine, so we have a little limitation, especially in peak hours. The good thing about nuclear power plants, they run 24/7 over the clock, and we never shut them down, so it's very good for stability of the grid. And also hydro as well. You can open a dam anytime that you have um, a power you know uh, need. You need more power, and it's good for the stability again of the grid. So the future grid will probably have a lot more renewables, but it will still need resources that can support the system. We're gonna have a mix of system, and in addition to that, we're gonna have a lot of storage systems like batteries and uh, hydro storage and so on. Now let's move into hydropowers. This is one of the oldest renewable energy technologies, and honestly one of the most useful in power systems because it can generate electricity, and in many cases uh, it responds very quickly. So it's very easy to open a dam and quickly compensate for the drop in generation and from other sources. Now, hydropower is just power generated from moving water, as you know. Uh, the way that it works, water at a higher elevation has potential energy, gravitational potential, and when it moves downward, the energy can be converted into mechanical energy, and then using a turbine from the mechanical connected to a shaft or a generator, then it will be converted to electrical energy. The two main things that matter are how much water is flowing and how much height difference there is. That height difference is what we call the head, the water head as well. Again, you can read faster than I can, so I just gave you a broad explanation. And obviously, because it's renewable, you have no fuel costs, and the fuel water is not actually consumed. You just use the energy of that. Now, hydroelectricity is electricity generated from hydropower. It has been around for a very long time and is used all over the world. Actually, the first power generation systems were hydropower and hydroelectricity. Um, and in fact, hydro has historically been one of the largest renewable electricity sources globally. So even though solar and wind get a lot of attention today, hydro is still a majority of production of renewable generation systems. Now, this shows the Niagara Falls. It's one of the classic examples of hydropower. It's a natural location with a huge amount of flowing water and elevation difference, which makes it excellent for generating electricity. It's also historically important in development of hydroelectric power. One of the first hydroelectric power uh, was actually created on this, if you go back to the history. There are different kinds of hydropower systems. We have hydroelectric dams, runoff river systems, pumped storage, small hydro, micro hydro, and even tidal power. They all use water, but they differ in terms of scale, storage, flexibility, and where they can be installed. Now, the this slide is an interesting slide because it shows that many of the world's largest power plants are hydro power plants. That tells you hydro is not just renewable, it can also be extremely large scale as well. And some hydro plants are absolutely massive. You can see the biggest hydro dams, the largest hydro dams in the world, and and actually this table shows you the largest power stations by generation capacity, and you can see from 10, 8 of them are hydro and one is nuclear and other is coal. The largest power station is a hydro dam, the Three Gorges dams in China. The installed capacity is 22,500 megawatts or 22 gigawatts. It's huge. And you can see that the other dams are in the next place, and only the Kashiwazaki plant is ranked number 6. So as you can see, 8 of the 10 largest power plants are in the form of hydroelectric. Actually, the Three Gorges Dam, when it was built and the reservoir was fully, you know, filled up, they said it had an effect on the Earth's rotational speed. That it's that big that it's creating actually a lot of environmental problems as well. Now, uh, this slide um, is shows some specification of the Three Gorges dams. The Three Gorges dams is one of the most famous hydro projects in the world. It's huge in size and huge in capacity. This is a good example of how power hydro can be when the site conditions are right and the project is developed at a very large scale. Uh, these are some specifications. The height is 181 meters or 597 or almost 600 feet. Length is about 2.3 kilometers. Width is 40 meters. It was fully functional in 2012. It has 32 main water turbines. Each has a capacity of 700 megawatts. It has two smaller generators to power the plant itself, so 100 megawatt just to power the plant. It's the world's largest power station in terms of installed capacity. The dam generated 98.8 terawatt hours in 2014 and had the world record, which was surpassed by the Itaipu Dam, which sets the new world record in 2016, producing 103.1 terawatts. Now these show some pictures, and at the end you can see this is actually an elevator that is used for a ship to go from the lower side to the upper side, and the ships actually come from here and go to this elevator platform. It's the largest elevator of its kind, and it just moves the ships uh, upstream. And you can see that it had a huge environmental impact because the fishes no longer can go upstream. And yeah, and you can see here this actually shows the scale of the dam. Uh, Sometimes we see just numbers like megawatts or dimensions. It doesn't really show the actual scale. But when we look at the pictures, you can appreciate how big these systems really are. Now, at the center of hydro generation is the turbine. Water flows through or in onto the turbine. The turbine spins. That mechanical motion drives the generator. The three main types we talk about are the Pelton, uh, Francis, and Kaplan turbines, and you can see the different types. There's a Francis turbine and Pelton turbine and the Kaplan turbine. Each of these are designed for different uh, applications and also um, different power capacity. Sometimes they are for hydro and micro hydropowers. Some of them are for larger dams and so on. And some are just for uh, specifically designed for different water speeds and uh, water hits. So for different applications, we have different designs. Um, Now, these turbines are used under different conditions. As mentioned, Pelton is typically for high head systems. Um, Francis is for medium head, and Kaplan is for low head. These are like usually micro dams and inline river systems. And Kaplan, as mentioned, is for low head but high flow systems. So engineers choose the turbine type based on the site and water conditions. And you can see that Peloton usually are uh, they operate best with heads from 15 to 1800 meters. Francis turbines, they are medium head, operate in waters head from 40 to 600 meters, and Kaplan turbines are head low or low head systems. Head ranges from 10 to 70 meters, and the output ranges from 5 to 200 megawatts. So they're small and micro scale. Now, this is the basic hydropower equation. The theoretical power depends on water density and also flow rate, gravity, and head. So, in simple terms, more water flow and more height difference mean more power. Then in real life, we multiply by efficiency because the system is never perfect. Obviously, water is the same, where rho is the water density, as mentioned, 1,000 kilograms per cubic meter. Q is the water flow rate. It's measured in cubic meter over seconds. And G is the acceleration of gravity, which is 9.8 meters per square seconds. Again, these two are fixed. H is the falling height or hydraulic head. Head is the height difference because between the inlet surface and the outlet surface. So the only things that we have control of is the falling height of the system and the amount of water that is passing. Now, as mentioned, the power captured by water turbine isn't like 100% efficient, so therefore we measure it in efficiency, where mu is the water turbine efficiency itself. Now, this is the standard hydroelectric dam setup. Water is stored in the reservoir. Flow through the intake and penstock spins the turbine. So we have the intake. Usually you have a filter or mesh system to prevent the debris and garbage to go into the penstock and into the turbine blades. And then the generator produced turbine is connected to a generator through a shaft, which produces electricity. The reservoir is important because it gives us some control over when and how the water is released. And usually we have a valve here that we can control how much water and when it's released. Now, the difference between the outlet and the inlet in height is called the hydraulic head. This figure shows the main pieces of a hydro plant more in detail. When I explain the slide, I usually walk through the whole process of the reservoir, intake, the penstock, and the turbine itself, the generator, the transformer. Obviously, you need to step up voltage, then step down the current to reduce your losses, and the power lines itself out to the grid. This is a very good overall picture of the system, and you can see the different parts mentioned here as well. Now, this slide gets into the reservoir balance. Basically, the water volume in the reservoir changes depending on how much water comes in, how much is discharged from generation, and how much is spilled. This matters because hydro plants are not just generating electricity, they are also managing stored water over time as well. And one actually benefit, or one of the applications that we use hydroelectric dams is for controlling floods. And some parts they are just for controlling floods and used as a reservoir. They are not even used for power generation. A lot of the dams are just used for water and soil management to prevent soil erosion and also floods, and also for drought seasons to store water, but they are not even used to generate electricity. Now, the discharge QJ is a function of hydropower pH. You can see the J is the interval, Rj is inflow during J, volume at end of J is Vj, Qj is discharge during J, Sj is the spillage discharge during J, Nj is the number of hours in interval J, and the units are acres feet per hour, acre feet per hour, acre feet per hour, and hour. And if you want to make the model very, very accurate, you would also add evaporation in the system as well. Um, Now, here we have multiple hydro plants connected along the same river. So the water leaving one plant becomes inflow for the next one. That means these plants are connected not just electrically, but hydraulically as well. So their operation has to be coordinated in these systems. So you can see that one of them has become the input on the other, and the other, and so on. And SJ is the spill rate over the dam's spillway, QJ is a hydro plant discharge, and NJ is the number of hours in each scheduled period. Now, another type of hydropower is runoff river hydroelectricity. Runoff river systems don't have much storage. They mainly use the natural river flow as it comes. Because of that, they depend a lot on seasonal water. So in spring, when the snow melts, you're gonna have a lot of water, and in fall, depending on the area, by the way, you're gonna have less. And because of that, they depend a lot on seasonal water conditions. They can be simpler and sometimes have less environmental impact than large dams, but they are also less flexible and they produce less energy as well. Now, this slide shows that runoff river system can still be pretty large. They may not have the same storage capacity as major reservoir dams, but they can still produce significant amounts of electricity. And these are some examples of the stations. Maximum capacity is like 3 gigawatts or 3,750 megawatts. And you can see big ones are in Brazil, Canada, and US. Now, another type of hydropower systems are the offshore hydropower or tidal power, we call them. Tidal power uses the movement of ocean tides to generate electricity. One nice thing about tides is that they are more predictable than wind or solar. You're gonna always have them. You don't care about a drought or rainy season. But the challenge is that tidal systems can be expensive, and there are fewer suitable locations, so they are not as widely used. And they are susceptible to corrosion because you usually have seawater, salty water, so the blades must be made out of special material. They need more maintenance, and so on. And these are some examples of them. They are mainly, and I would say, the prototyping and proof of concept phase. They're not very large. The largest one is in South Korea, 250 megawatts. It's relatively small in hydropower scale. Now, another type of hydropower systems are the pump storage hydroelectricity systems, which have gained a lot of traction in the recent years because of rise of renewable energy and the need for storage systems. Um, and these pumped power storage systems are really important in modern power systems. Think of it like a giant water battery. When electricity is cheap or there is extra power on the grid, water is pumped uphill. And when the electricity is needed later, the water is released back down to generate power. And these account for 95% of all utility scale energy systems in the US currently, because they could be built in large scale and much cheaper than lithium batteries or chemical batteries. But again, you can't put them everywhere. You need to have like two reservoirs, and they are very expensive to build in the first place. Now, the way that they work is that is shown in this slide. And this slide shows the difference between the open loop and the closed loop pump storage. By the way, we have two types, open loop and closed loop. I forgot to mention this. Open loop is connected to a natural water source like a river. Closed loop is more isolated and not directly tied to a natural flowing river. That difference matters for environmental and operational reasons. Um, One thing students sometimes find confusing here is the negative energy number. The reason is simple. Uh, Pumped storage uses more energy pumping water uphill than it gets back later when generating because there are losses in the system, obviously, and the efficiency of the pumped and the generator is not 100%. But it's still very valuable because it shifts energy from low price times to higher price times and helps the grid stay balanced. Um, and these are some numbers, by the way, for hydropower. In 23, the global pump storage hydropower capacity was 182 gigawatts, with China leading with 50 gigawatts of that. Japan and the US followed with 21.8 and 16.7. The US PSH fleet currently consists of 43 plants with a combined capacity of 22 gigawatts. And as you can see, the negative number again because the efficiencies are typically around 50 to 80%, but still it's very valuable. Um, this is a real pump storage facility, shows the graph of it. It's helpful because it gives you a physical picture of how the system is laid out. You have the upper reservoir, the powerhouse, and the lower reservoir. The plant can move energy back and forth depending on the system's need. You can see the discharge, the reservoir intake. Again, it's exactly like a dam. It's an artificial dam. Usually they build it on top of a mountain. And you can see the different parts of the system. Um, Now, this is the Glen Canyon Dam in Arizona on the Colorado River. It's another good real world example of major hydro infrastructures in the US. It also reminds us that rivers often have multiple dams, so hydro operation can affect a whole chain of facilities. And you can see the Colorado River and um, different parts of the dam. Now, these images here, I put them here because they give you a better feel for the dam and the equipment inside. It's like a city inside. Actually, you may think it's actually hollow, and you have all the generators and everything inside. It helps students see that hydropower is not just a simple idea. It's a huge engineering system involving civil, mechanical, and electrical components. You can see the turbines, the generators, the grid, and so on. And we have different type of, by the way, dam systems. I'm not going to get into them, but depending on where you put them, if it's a rocky or sandy system, you're going to put different type of dams. This example shows why pump storage can still make money even though it loses energy overall. It buys electricity when prices are low and sells when prices are high. So even when efficiency losses, it can, even with the efficiency losses that we have, which is around 30%, it can still be profitable because the timing of energy matters. This gives us two intervals, night and day. Efficiency is 70% for this example. Electricity prices 10 cents per megawatt hour, $10, I'm sorry, per megawatt hours at night, and 30 per megawatt hour in the day. And use this as the usual normal because at night, no, everyone is asleep, no one is using power. The power is much cheaper. The pumping power is 100 megawatts, and the cost at night would be 12,000, and the revenue in the day would be 25,200. So you're gonna get 13,200 in net profit and profit. And energy generated in one cycle is going to be negative 300 megawatt hours, but still again because we're using this as a storage and we're shifting today, we're gonna still benefit in the system. Now, hydro is great, but it also has limitation. It depends on water availability, so drought can be a big problem. Also, water has to be shared with other uses like agriculture, irrigation, recreation, and environmental protection. So hydro plants can't just operate however they want. Now, one of the best things about hydro is flexibility. Hydro units can ramp up very fast, often much faster than thermal plants. They take a couple of hours sometimes. They make that makes actually really useful for balancing the grid, handling sudden changes in demand, and supporting variable renewables like solar and wind. Now this slide shows a simplified model for pump storage in terms of storage energy and power. We have it in generation mode and pumping mode. The equations also include limits on stored energy and power. You can see the constraints that we have. And these kinds of models are used in scheduling optimization studies. Pmax here is the maximum power for both pump and generation, and mu is the efficiency losses when occur when a pumping assumptions here. And the parameters of lower reservoir, we have the maximum energy and the minimum energy. And parameters of maximum energy and minimum energy for the upper reservoir and for the lower reservoir are mentioned here. So overall today we looked at renewable energy in general and then focused on hydropower. We talked about how hydro works, different types of hydro system, turbine types, pumped storage, and some of the main pros and cons. If you have any questions, just please email me. Next week we will continue with renewable energy and energy storage, and we will finish with smart grids and microgrids. Thank you so much and have a great week.